Hey guys, so starting with section 5.3, it's dealing with inverse functions. This is something that you guys learned back either in Algebra 2 or pre-calc. So our objective is to verify whether one function is the inverse of another, to determine if a function has an inverse, and then find the derivative of the inverse. This is the right here, that's the new stuff, okay? Finding the derivative of the inverse. Now, the notation for the inverse is f, and it looks like it's raised to the negative first power, but that means the inverse of f. And if f and g, if two functions f and g are inverses of each other, then algebraically, if you compose the one with the other, meaning you put one inside the other and vice versa, you should get x out of it. Graphically, if you graph a function and its inverse, they should be a reflection over the line y equals x, meaning that the x and y switch. So the domain of f, that would be the x values, would be the range of g, which is the y values, and vice versa. So if you have the point like 1, 2 on a function, its inverse would have the point 2, 1. Every function does not necessarily have an inverse. To tell if a function has an inverse, you basically go to number 3. That's the most important thing. It must be monotonic. So that's a new vocab word for you guys. And monotonic means that the function is always increasing or always decreasing. So it always has to be going in the same direction. So whether it's always increasing or always decreasing. So to tell if a function is increasing or decreasing, you look at the derivative, right? The derivative tells you if a function's increasing or decreasing based on the sign of the derivative. If the derivative is positive, that means the original is increasing. If the derivative is negative, that means the original is decreasing. It's as simple as that. So with example 1, we want to know if this function has an inverse. We don't have a calculator to graph it to see if it's always increasing or always decreasing. So we're going to take the derivative. So derivative would be 5x to the fourth plus 3x squared plus 3. And you think about this, okay? No matter what x is you plug in, the derivative will always be positive, right? No matter what x you plug it in, whether it's positive or negative. And if you add 3, this is always going to be positive. So that means that the original is always increasing. And if it's always increasing, it therefore, and this is the symbol for therefore, it's a triangle with 3 dots. Therefore, it has an inverse. Just bear with my writing here. Okay, so if you can prove a function is monotonic, meaning always increasing or always decreasing, then you know that that function will have an inverse. Okay, now, how do you find an inverse? To find an inverse, you are going to switch the x's and y's and solve for y. And now that I'm looking at it, we actually don't do this in accelerated calc, find a derivative of the inverse. So don't even worry about that. Okay, we're just reviewing inverses at this point. So how to find an inverse, what you're going to do is switch the x's and y's and solve for y. So here, this is normally y equals, so we're going to make it x equals square root of 2y minus 3. So we switch the x's and y's, and now we want to solve for y. So to solve for y, you are going to get rid of the square root by squaring both sides. So then what you get is x squared equals 2y minus 3. And then we're going to add 3 to both sides. So x squared plus 3 equals 2y. And then we're going to divide everything by 2. So we get y equals x squared plus 3 divided by 2. So this is the inverse of the original function f of x. So we're going to do the same thing here. We're going to switch the x's and y's. So the x's become y's, and the f of x, which stands for y, becomes x. All right, and we got to get y by itself. So we're going to multiply through by y, 3y. And then you have y's on the left and y's on the right. So what you want to do is get them all to one side. So I'm going to subtract the 2y. And then what do you think I'm going to do on the left-hand side? I'm going to pull out a y. And now I can get y by itself. And y equals 1 divided by 3x minus 2. So here's your second inverse. Okay, this is the inverse of the original function. And the last thing for today is check your answer for example 2, so this example, by using the algebraic proof. So you have two functions. So we'll call the first one f of x equals root 2x minus 3. And then we'll call the inverse that we found g of x. It's just easier to define it like that. So that's x squared plus 3 divided by 2. Compose, the algebraic proof says that if you take a function and its inverse and you compose the two, either way, f composed with g or g composed with f, you should get back x. Okay, that's how you know two functions are inverses of each other. So we're going to do it both ways. So let's start with f of g of x. So that means we take g of x, we take this right here, and we plug it in. I'm going to take this, and we plug it in for the x in f. Okay, so that's going to give us root 2 parentheses. So I'm plugging this in for x. I get x squared plus 3 over 2. And then I minus 3. Okay, so the 2's will cancel. The plus 3 and the minus 3 will cancel. You're left with the square root of x squared, which equals x. So the one way works when you compose f with g. All right, let's go the other way. G of f of x. Okay, so now what we're doing is we're taking f of x and we're plugging it in for the x of g. So we're taking the root 2x minus 3, and when I plug it into the x for g of x, I'm squaring it. Then I'm going to add 3 and then divide by 2. So when you square a square root, you just get the inside, right? So now what's going to happen in the numerator? The 3's will cancel, the 2's will cancel, and you're left with x composing that way too. So we just proved that in example 2, this original function and this one that we found is the inverse are certainly inverses of each other because we compose them both ways. That's the algebraic proof. Now, if I were to graph them, they would be a reflection over what line? They would be a reflection over the line y equals x. Okay, so that's section 5.3. I'm just going to look briefly here. 5.4, we are going to do the next day. All right, thanks, guys.